Hello and good day. In this short video, we hope to take your interest into our experience, admiration, and fear for auto machine learning. First, AutoML will be introduced. Second, we would like to go deeper into the process. Third, the existing use cases are explored. And lastly, we will go into future works. We start with a well-known traditional machine learning pipeline. If you like, you can follow our example with the QR code to a Google Colab implementing a classical pipeline and an AutoML pipeline. Our example represents a dataset of emails where we want to detect spam. We chose this example since natural language processing is a hot and difficult topic. The first step in the classic pipeline is data acquisition. Second, to create good decisions, the data must be explored. This shows that we have to deal with an imbalanced dataset with primarily non-spam data. We also find some interesting information that spam mails are mostly longer in length. The third step is data preparation. In NLP, sentences need to be cleared up to lowercase, remove punctuations, weird symbols, etc. Then stop words have to be removed and so on. All this is done by first cleaning, which sets text to lowercase, removes the text in square brackets, etc. Afterwards, stop word removal, and lastly, stemming. Next up, feature engineering puts the words into vector spaces. Lastly, the tedious and iterative task of model selection, model training, and hyperparameter training is performed. As a result, our predictions are made. All these steps need a lot of knowledge and time. But what if I told you it could be simpler? That is what AutoML does for you. You have the data, then you have a model. No feature engineering, no data exploration, and no hyperparameters to tune. Only your data, your labels, and you get the result. So, how does it actually work? The first step of AutoML is data preparation. The system will ask itself, is there enough data? If the answer is no, data collection will be performed. If there is online data available, open datasets will be used and filtered to derive extra data. If there is no online data, data synthesis will be performed. The most novel technique for this are generative adversarial networks. Once there is a sufficient amount of data, the system will again ask itself, is the data clean enough? If not, data cleaning will be performed. The most automated approaches are boost clean and alpha clean. There is, however, an optimization problem if the data is continuous. The final step is data augmentation. Automatization of this is computationally quite expensive. To increase the efficiency, techniques like gradient descent, Bayesian descent, or greedy descent are used to select the augmentation techniques. The next step is feature engineering. AutoML uses a dynamic combination of three techniques. The first is feature selection. This approach generates a subset of the original features based on a search strategy. Afterwards, the features get evaluated. If the evaluated features match or exceed the stopping criterion, they get validated. If the evaluated features do not match the stopping criterion, another subset is taken. These subsets form the new features. The next technique is feature construction. Here the features get transformed into new features by using methods as standardization, normalization, or discretization. These methods use operations like conjunctions, means, Cartesian products, and more. And the third and last technique is feature extraction, where mapping functions are used to achieve dimensionality reduction. Examples of this are principal component analysis, neural nets, and autoencoders. The third step is model generation. Model generation will find a suitable model and tune it. In this video, the focus lies on deep neural networks. Model generation can be split into two parts. The first is search space. In this part, the type of the neural net is chosen. It can vary from cell-based, hierarchical, morphism-based, or entirely structured-based. Once a network type is chosen, the architecture of the network gets refined to a concrete design during architecture optimization. Once the design is chosen, the hyperparameters are tuned to achieve maximum accuracy for the model. The tuning of the parameters can be achieved using multiple techniques. The most common are reinforcement learning, evolutionary-based algorithms, gradient descent, or Bayesian-based. These techniques adjust the parameters in a smart and recursive way. The final step is evaluation of the models. The network is trained and evaluated. However, this step would require an excessive amount of computation time and resource usages if it had to do this for every model. As a result, a few solutions to streamline this process have been proposed. The first is low fidelity. This technique lowers the quality of the data, for example, a lower image resolution. It also reduces the model size, for example by using a lower filter size. A second technique is early stopping. Here the evaluation of the model is stopped early if there are signs of a bad accuracy. Another method is a surrogate model. This technique tries to approximate the black box function and predict its results. Good predictions will then be further evaluated. And lastly, weight sharing. This method uses knowledge from previous models, the weights, and uses good weights to increase the speed of the process. Now let's talk about the main advantages of AutoML. The first is of course the accessibility. Users do not need to have an extensive amount of machine learning knowledge to find a solution. Only a simple basic understanding of programming might be enough. The next advantage is the time friendliness. Since AutoML does all the parameter fine-tuning and the design of the model, user will not need to spend countless hours training his model to find a good performing one. AutoML also achieves a high accuracy. This is made possible by the vast amount of different models and parameters that are explored. These two advantages allow users to easily create an advanced baseline and also give model exploration and analysis. A last advantage is the fact that AutoML keeps up with all the up-to-date techniques in machine learning. Next up, the limitations of AutoML. The first two limitations are caused by the black box principle of AutoML. Since everything is automated and mostly in neural networks, the user will not be able to see why certain features were selected or why certain parameters were tuned the way they were. The user will also have very little customization options since the pipeline delivers a complete model. Another limitation is the performance of AutoML on new data. Since data collection of new data will not be as effective as older data, the amount of data for the models to work with will be limited. And the last but important limitation is the false sense of security AutoML gives. Users should stay critical about the results since AutoML cannot tell you for certain if the created model is 100% trustworthy. Now that you know how useful this tool is, you can easily get to work. If you still need to tune a model for a course or a thesis, just put in your raw data into the AutoScaLearn classifier to tune fast models within limited time. Or for stronger neural networks, use AutoKeras. We tested it with our example of spam mails in the beginning and obtained outstanding results, which seemed to be a state-of-the-art BERT model without even having a glance at learning rates, layers, overfitting, etc. It is all performed by itself. Non-programmers, no fear. Google provides a cloud service to people with zero coding experience, for a price of course. If you have the data, they provide a strong model, which can be optimized with some tools they provide to analyze the mistakes, like false positives or false negatives. Google is, of course, not the only one. Some other well-known industries are DataRobot, H2O AutoML, and of course all big tech companies like Amazon and Microsoft. But how about real practices? A good example is in the healthcare industry, to predict a patient's outcome and identify a patient's risk to develop certain diseases. AutoML has also been used in the financial industry, to predict stock prices and detect fraud. To conclude, it is very useful in industries with a lot of data. And on top of that, it is really fast and easy to provide prototypes, and therefore limited downtime when new models are mandatory when big changes occur. Lastly, the future works of AutoML. How impressive AutoML already may be, there are still some problems left to solve. The first is the exploration of new tasks. AutoML will be efficient on traditional tasks such as image classifications, but other tasks might still be difficult to achieve. The next problem is robustness. Most of the neural nets have performed well on research datasets with a small amount of noise. However, real-world data might fool the neural networks. Another problem occurs when new data is entered. AutoML should try to use other models to help aid in forming a model for this new data. A fourth problem is the visibility. This problem was also mentioned when talking about the limitations of AutoML. The choice of the system are hidden from the user. Solutions to view and maybe explain these choices could be of great value. And the last problem is the tendencies of AutoML to overfit on the given data and as a result perform subpar for new real-world data. Doubtless there will be more and more improvements of AutoML, and more research will be done. It will however always be necessary for society to have people around that understand the models, since new data and new tasks constantly arise. So do not be afraid yet, for the next couple of years AutoML will probably remain a tool to help developers instead of replacing them.